So in today's video, we are going to be taking a look at what the force of gravity is and how it creates planetary orbit. So we'll start out by reviewing what mass is and how it affects gravity. So all objects that have mass also have gravity, as stated by Newton's law of universal gravitation. So as a review, mass is the amount of atoms in an object. So to say something that has mass has gravity means that any object made up of atoms or molecules also have some force of gravity. Gravity is defined as the natural force of attraction between all objects. And every object in the entire universe has gravity, whether it's a skittle, or a school bus, or the chair you're sitting in, or the desk you're working at, or the laptop or computer you're watching this video on. All of these objects have gravity no matter how small. However, the larger an object is, or the more mass it has, the more gravity it has. So every object bends space around it, which causes other objects to sink towards it. This is what gravity is. It's this bending of space. If you look at these pictures here, you can see the space is bent inwards. Look at what this looks like as this ball is rolling across the surface. Imagine space as if it were a bed sheet. Say you and 3 of your friends take a bed sheet and stretch it out. Each one of you grabs one of the 4 corners and you stretch it out flat. And then you're going to take a bowling ball and put it in the center of that bed sheet. The bed sheet would sag in the middle. So if that bed sheet represented space and that bowling ball represented some kind of center of gravity, well, that dip inwards that would be created in the bed sheet is what gravity is. So this picture symbolizes it right here. This is our bowling ball. This grid is our bed sheet. Look how it sags in the middle. So imagine you were to try to roll a ball across that sagging bed sheet now. The ball wouldn't roll straight across. It would curve a little bit around that bowling ball. And that's what happens out in space. So when an object has a lot of mass, it sinks a lot of space inwards. Look at this picture right here, which represents some sort of planet. It looks a little bit like Earth. It's an Earth-like planet, and it sinks space inwards. So the larger an object is, the more space it would sink inwards, meaning the more gravity it possesses. So yes, all the objects around you, looking around the room right now, bend space in some way, but they bend it in such a small amount. This planet bends space in the largest way. So that's why Earth is what affects all of us. We don't experience the gravity from our computers, the gravity from people around us, because they're not nearly as large. The largest object to us is the Earth. So the Earth, being the largest object, has the most gravity, and it's the only gravity that we ever really notice. That would explain the joke in Family Guy when Peter Griffin has objects orbiting around him. The joke is that he's so fat that he has his own orbit because his mass is so large that he has objects orbiting around him. Brian also has mass, but he's not fat enough and not large enough to sink enough space inwards to get objects to float around him. So the largest object in our solar system is the Sun. The Sun has the most mass. The Sun is what has the highest gravity. So we're right here on Earth. We experience the Earth's gravity because the Earth is what's closest to us, and we'll find out in just a minute that distance also plays a role in the strength of gravity. But if we were closer to the Sun, it's possible that we'd be pulled towards the Sun because the Sun has such high gravity. So the Sun has a high enough gravity that all of these objects, as far out as Neptune, are sucked into this bend in space that the Sun creates. They're bent inwards and they're moving around the Sun as a result of the bending inwards of space, as are we here on Earth. So that's one thing, is that mass has an effect on the strength of gravity. So now let's talk gravity and distance. That's the other effect of the strength of gravity. So objects closer to the center of gravity will experience a stronger gravitational force because the bend in space is steeper. Objects are drawn into the center of gravity more strongly. So let's look right here. If there's an object out here, here's some kind of planetary object out here in space. Now, if it's out here, it's eventually going to get pulled inwards by this planet's gravity. But they might not be experiencing that strong of gravity because it's right around the edge of space. If there's an object out here, it's not really, look how it's not really falling into that dip inwards. It's very far out of the realm of this planet's gravity, so it's possible that it might not even be affected by the planet's gravity in any real way. However, if we have an object right here, look where that falls in the pull of the gravity. Now it's right here in the center. It's going to be pulled very strongly by the gravity, and if it's even closer, it's going to be pulled even more strongly. So the idea is the closer you are to the center of gravity, the stronger gravity you feel because you're further in this dipped in bowl. You're further in the pull of gravity. So now planetary orbit. There's two factors that go into creating planetary orbit. You've kind of been seeing images of it, how a planet could move around another one. So orbit is when an object travels around another object in a fixed path in space. Gravity is one of two of the main forces that make orbit possible. We've learned about two factors that affect gravity, both mass and distance, and both of these have an effect on orbit. However, there's another force that also is needed for orbit to be possible. Inertia is the second force that is needed to create orbit. Inertia is defined as the force of a moving object to continue moving in the same direction unless stopped. So the idea is that when you're moving forward, your body or any moving object wants to continue moving forward. Unless it's stopped by some kind of force, something will continue moving forward. So, for example, look at this car. You might have not been in this exact situation, hopefully, where you're flying out of a car, wear your seatbelt. But you may have felt this before when you're sitting in a car and you're in the back seat and the car stops short and you feel a pull forward on your seatbelt. That's inertia pulling you forward. Your body wants to continue moving forward. However, it's stopped by the seatbelt. So on Earth, we're stopped by a number of things. There's a reason we don't just keep on moving forward. If we start running, we're able to stop. Because on Earth, on the ground, we are stopped by Earth's gravity pulling us down. We're stopped by air resistance, so we're either pulled down or there's air resistance pushing back on us to stop our inertia. So one of these two forces usually ends up stopping us from moving. But out in space, there's not as much to stop the inertia. So if you look on this next slide here, you'll see that objects in space will continue moving forward forever unless they crash into something or they get pulled in by a planet or star's gravity. So let's take a look at this planet right here. This object will continue moving forward due to inertia. There's nothing to stop it. There's no air out in space. If it's far enough away from gravity, there's literally nothing to stop it. Physics tells us that this object will continue moving forward indefinitely until it's stopped by something. It's going to continue moving forward forever. However, if it draws close enough to some kind of gravitational pull, in this case we have the sun, if it draws close enough to this pull, it ends up getting drawn into the orbit. It ends up getting drawn into that gravity. Remember that bowl of gravity that's created? It ends up getting drawn into that and starts to move around in the circular path. It can no longer move forward in a straight line. It starts to move in this path because its Earth's gravity is pulling it inwards. Let's look at a second picture to show us how these two forces work together. So an orbit is created by the equal forces of inertia pushing an object forward and gravity pulling it down. So imagine, if you will, a planet. This is our center of orbit. This is our C for center of orbit. And we have a planet flying through space. Maybe it was broken off by some kind of meteor strike. Maybe there was some kind of mass core explosion. For whatever reason, this planetary object is moving forward in space. Its inertia, this red represents inertia. Its inertia is pulling it forward. So it's been flowing forward for billions of years. And it happens to cross the path of some kind of center of orbit, something with strong enough gravity to pull it downwards. So this inertia is no longer strong enough to keep it pushing forward. It gets stuck in this well of gravity. Remember those wells of gravity? So now, instead of going forward, it creates this third image right here. Yes, the inertia is still there, pushing it forward, but now there's also the second force pulling it constantly towards the planet. And these forces are in balance. That's why the planet doesn't crash into the center of orbit. That's why we don't crash into the sun. Because our inertia is pulling us forward with the same strength that gravity is pulling us down. So the inertia of our planet is equal to the gravity that we're experiencing from the sun. So when these two forces equal one another, it creates this pink line right here, which would be orbit. These forces are in balance. They keep the planet in the same spot. That's why the moon is not crashing into the Earth. That's why we're not crashing into the sun, because inertia pushes us forward and with the same strength that gravity pulls us down. So there's 3 laws developed by the German astronomer Johannes Keppler that describe the way planets orbit the sun. You will definitely hear a lot about Kepler's laws as you progress in science. Kepler's laws are the famous laws when talking about planetary orbit. They're spoken about very frequently when discussing physics. So the first of the 3 laws states that every planet orbits in an ellipse. That's this word right here, in an ellipse, or an oval shape. That's what it means. It's an oval shape, not a perfect circle. When you imagine Earth's orbit, you probably imagine in your head a perfect round circle, but the truth is it's more of an oval shape, and the fancy word for that is an ellipse, not a perfect circle. And every planet that orbits has an ellipse. There's no planet, there's no object that orbits in a perfect circle. So every object that's experiencing orbit is orbiting in an oval or an ellipse. There's no perfect circles when we're discussing orbit. That's the first of Kepler's laws. The second law states that a planet moves faster when it's closer to the sun or center of orbit than when it's farther from the sun or center of orbit. So just look at 1 rotation or 2 rotations of this picture right here. So watch how the speed changes. The planet revolves further away from the center, and then when it moves closer, watch the speed increase right here. You see that? Yeah, that's due to the fact that it's experiencing stronger gravity. When it's experiencing stronger gravity, it will move faster. So that's our second law, is that a planet moves faster when it's closer to the center of orbit than when it's farther away. Finally, our third law, and where we'll end, is that planets farther away from the sun take longer to travel around their orbit. If you look at this picture, look how many times the red planet can orbit in the same amount of time that the blue planet along the outside orbits. The red planet orbits 4 or 5 times before even this second blue planet right here is able to orbit. So the closer an object is to the center of orbit, the faster it will move. And that plays right into Kepler's second law, the idea that something closer to the center of orbit will move faster.